This is section 10.3. We're finding area of polar curves, area inside a polar graph. For a very small theta, the curve could be approximated by a straight line, and the area could be found using the triangle formula, area equals 1/2 base times height. Now take this circle, for example. It could be other different curves as well. If we have this angle, or this, let's say this arc length right here, we could approximate this arc length right here using this line, especially if the angle became very small. If it was a little smaller, or even a little smaller than that, the line would get closer and closer to the actual length of the curve. Now in calculus, when we integrate, that's what we're doing. We're adding up in infinitely small amounts and getting this solid object. Well, the derivative of the area equals 1/2, or the area of this triangle. We have 1/2 r d theta times r equals 1/2 r squared d theta. If we integrate both sides, these are going to be angle values, or theta values. And usually we pull the 1/2 to the outside so we don't have to mess with it. But this is what you got to remember right here. 1/2 r squared d theta, and we're using the area of a triangle to find the area of these objects. We're going to run across a problem in finding the integral of cosine squared. It's very difficult to do that unless we use our double angle formulas. Cosine of 2 theta equals 2 cosine squared theta minus 1. If you add 1, divide by 2, it turns out that cosine squared can be turned into 1/2 cosine 2 theta plus 1/2, which allows us to very easily take the integral of this. It's tough to take the cosine integral of cosine squared, but this one is just going to be 1/4 sine of 2 theta plus 1/2 theta, and we got it. We're going to do the same thing with sine squared. We're going to isolate sine squared, turn it into 1/2 minus 1/2 cosine 2 theta, and find the integral of this. Is fairly straightforward. Our first example, we have find the area bounded by the graph of r equals 2 plus 2 sine theta. Here's the graph, and I want you to imagine a magic windshield wiper. And it's magic because it's going to swipe around this object, but it can change lengths. So it's a magic windshield wiper that can change lengths. And imagine taking all of the windshield wipers and adding them all up, you get this solid object, and you could find the area. And here, the length even gets 0 at 3 pi over 2, and then gets a little longer until we get all the way back to 2 pi again. This object will finish in 2 pi, so we're going to integrate from 0 to 2 pi. And here's the formula of that triangle, 1/2 r squared d theta. So we're going to square the function 2 plus 2 sine theta. We can do that by foiling. And I've factored out a 4 and made the 1/2 into just a 2. Half of 4 is 2. But we're having an issue right here, like I said before, with sine squared. But we're going to turn that sine squared into 1/2 minus 1/2 cosine of 2 theta. And then we can take the integral, and it just becomes, here I put 1 and 1/2 together and made it 3/2. And then we have minus 1/4 sine of 2 theta, and then finished out the integral right here, and our answer is 6 pi units squared. Now, of course, we can do the integral once you catch on that you can turn this to this. It's the setup that we're really interested in, being able to get this line right here. I think once you get this line, the rest is pretty basic up, in this point of calculus. Find the area of one petal of r equals 2 sine of 3 theta. So here we have a rows with 3 petals. At 0, we're at 0, and then this one petal is going to finish in pi over 3. Pi over 3. So here we have 0 to pi over 3 of 1/2 of the r squared. We have sine squared of 3 theta. And I've pulled out the 4 here, made it 2. So this is kind of an issue here. Well, let's examine this a little bit. We have cosine of 2 theta equals 1 minus sine squared of theta. Well, we don't have sine squared theta. We got sine squared of 3 theta. So we're going to make these thetas into 3 thetas. So we have cosine of 6 theta. and we make that 3 theta equals 1 minus sine squared of 3 theta. So when we minus 1 and divide by, whoops, I need a 2 there. When we minus 1 and divide by negative 2, we're going to get 1 half minus 1 half cosine of 6 theta instead of 3 theta. And that's how you make the replacement. The rest's pretty straightforward. Take the integral. You end up with an answer of pi over 3 units squared. And we found the area of this one petal. In our next example, we have find the area of one petal of r equals 4 cosine of 2 theta. And cosine starts over here at 1, but of course we take 4 times that, so we're out here at 4. And then it's going to loop, and it finishes this half of the petal. Remember, there's a magic windshield wiper going around filling in all of the areas. This is going to finish in pi over 4, just this part of it right here. And then we're going to loop all the way around the curves. And once it gets back to here, it's going to be 7 pi over 4 to 8 pi over 4, which is 2 pi. But instead of splitting it up into two integrals, this 7 pi over 4, here's your 7 pi over 4 right here, if you go in this direction, can also be considered negative pi over 4. So we can go from negative pi over 4 to pi over 4, and there's the 1 half, and usually we write that to the outside like I've done here, and squared the r. So we have 16 cosine squared of 2 theta, which when we make that substitution is going to be 4 theta. Then we can integrate, and we can come up with an answer of 8 pi units squared, units squared. In the next example, we want to find the area inside r equals 3 sine theta and outside r equals 2 minus sine theta. So let's see. 3 sine theta is in the blue, and 2 minus sine theta we've left in the black. So we want inside the circle and outside of 2 minus sine theta. So inside the circle, outside of the 2 minus sine theta, that's this area right there. Now, we're interested in this point and this point where they intersect. So if you set them equal to each other, you find out that they're intersecting at pi over 6 and 5 pi over 6. So what we're going to do is we're going to take this magic windshield wiper, and we're going to start it where they intersect. And we're going to fill in all of this area. Now, I know that's going to be too much, but then we're going to do a subtraction. If you look down below, we have a subtraction. And we're going to keep filling an area until we get to the other intersection point. Well, right now we are following this blue curve. That's what our windshield wipers are following, and it's filling in all of this area. Well, what we want to do now is go back over and use the windshield wiper again, except we're going to follow this curve now, and this area is going to subtract. So it's going to start at the intersection again, and it's going to start subtracting out this area, and finally we're going to be left with the area that we want. So when we do the minus, what we're really doing is taking away this little area right there, and then we'll be left with what we want, of course. And I'll tell you that the integration is just absolutely brutal. It's a mile long. So right now, take my word for it, it's going to be 3 square root of 3 units squared. Your homework isn't going to be nearly as long as this one was. But the setup is what we're interested in, and I trust right now that you can actually do the integral. In our last example, we have find the area of the common interior of r equals 3 cosine theta and r equals 1 plus cosine of theta. So blue is this graph right here, 1 plus cosine of theta, the common interior. So let's see how we would get this area with our magic windshield wiper. Well, we want the common interior, so it's really going to be the area that we're looking for right now is in this area right here. Now, we're going to start with our magic windshield wiper, and we're going to start on the 1 plus cosine of theta, and we're going to work our way around. And here goes the angle. We're going to keep working our way around until we get to this intersection point. It's not going to follow the blue curve anymore. It's going to start following the black curve, which is the 3 cosine theta. So then we start following this curve until we get to 0. Or it's not 0, until the windshield wiper gets to 0, but really it's going to get to 0 at pi over 2. So we want to start following the blue from 0 to the intersection point, and that intersection point is pi over 3. And then we want to follow the other curve from pi over 3 to pi over 2. So there we have it. From 0 to pi over 3, we're going to follow the blue with our magic windshield wiper. And then once we get to pi over 3, we don't follow the blue anymore because we want the common interior. We're going to follow the 3 cosine of theta, and that's going to go from pi over 3 to pi over 2. Now, of course, that's only going to be the top half of what we want. And to get the bottom half, well, this is symmetric, so we're just going to double it. And there's the work, and it's quite extensive. It takes a little bit to get this one done. But in the end, we end up with 5 pi over 4 units squared. And really, I trust if we can get this set up right here, and of course I've doubled it and used symmetry, I think the integration's not too bad, as long as we remember that the cosine squared of theta becomes 1/2 cosine 2 theta plus 1/2. And of course, I've pulled the 9 out right there. And you can look through this integration process.